In this video, we're going to look at a couple examples of writing nuclear equations for radioactive decay. We're going to look at alpha decay, beta decay, positron emission, and electron capture. Now, before I get to those examples, I just want to give a quick review on nuclear symbols. When we first did this, when we were introduced to atomic structure, we defined the left-hand superscript as the mass number. And this told us the number of protons plus the number of neutrons. And then the subscript on the left is the atomic number, and this tells us the number of protons. So the atomic number gives me the number of protons. If I want to know the number of neutrons, then I can just take the mass number, subtract from that the number of protons, and that tells me how many neutrons that particular isotope has. So in the case of sodium-23 here, I know that it has 11 protons, and then I know that it has 23 minus 11, that means it has 12 neutrons. Now when we do nuclear equations, not only are we going to have isotopes like this, but we're also going to be dealing with subatomic particles. So one of the subatomic particles is an electron. And so I've written the nuclear symbol here. Right? And so an electron has no protons and neutrons, so its mass number is going to be 0. And so in addition to thinking of the subscript as the atomic number, we can also think of this as being the charge. Right? So we know that protons are positive, electrons are negative, so the atomic number, if you will, of an electron is -1. All right, so we went through the subatomic particles that you need to know in class, but I've put this table here again. If you want, you can pause it and write these down or refer back to your notes. What I would recommend is maybe making flashcards because you'll want to be able to write these nuclear symbols from the names or know the names based on the nuclear symbols fairly readily. Okay, so in our first example, we want to write the nuclear equation for the alpha decay of thorium-231. And so one of the first things that we need to do is go to our periodic table and see what the atomic number is for thorium. Right? So they give us the mass number. The mass number is 231. And I find thorium down here, so the atomic number is 90. So if we go back, I can write the nuclear symbol for thorium is 90, and they told me the particular isotope we're dealing with is 231. So in most of these types of radioactive decay, I'm going to be starting with the parent on the left, then I'll have an arrow, and so we're going to decay into the subatomic particle that's being spit out plus the new daughter nuclide that we're going to make. And so this is where knowing the subatomic particles is important, because in order to finish this off, I have to know what the nuclear symbol for an alpha particle is. And so from that table, we know that an alpha particle is always a helium-4. And so now I can use this to figure out what the daughter is going to be. So there's only one other piece here. It's going to be what is the nucleus that is left after this alpha particle is spit out. And the way we figure that out is the atomic numbers on the right-hand side, so the 2 plus whatever this is, has to add up to be 90. Now, the same thing is true for the mass number. So whatever the new mass number is, it plus 4 has to be equal to 231. So doing some simple math, I can see that in order for the right-hand side to be equal to 90, that means that the atomic number of the daughter has to be 88. And in order for these two to add up to 231, right, that means 4 plus 227 is going to be the mass number of the daughter. And so I'm not going to go back to the periodic table, but I would encourage you, go ahead and get out a periodic table and go see what element 88 is, and then we can finish off this problem. So pause it, I'll give you a second. All right, so hopefully you found out that element 88 is radium. Now, when I figured out the atomic numbers and the mass numbers of the daughter, I just did that in my head. But it's easy to go the wrong way, right? So the correct answer here is 88, but it could be easy to make a mistake and make that 92. And so you can always check your answer, right? Once you get to the final result, make sure that, okay, 2 plus 88 is equal to 90, and 4 plus 227 is equal to 231. And let me show you just one more trick. If you're having trouble figuring out what the new atomic numbers and the mass numbers are for the daughter, you can write a simple mathematical equation, right? And so we're going to add up the numbers on the left-hand side. You can treat the arrow like an equal sign, and then have the numbers on the right-hand side, right? So I'm going to have 90 is equal to 2 plus x, right? Because there's the 88 that we didn't know before. And so now it should be pretty easy to solve this equation to get that x is equal to 88. I could do the same thing to figure out this unknown mass number. If I was having trouble figuring out what it is, I could say, okay, I'll do 231 is equal to 4 plus x. Right, to solve this, I subtract 4 from both sides, and so I get x is 227. Right, so this last bit was not strictly necessary. Right, I was just trying to show you, if you're having trouble figuring out what the new atomic numbers and the new mass numbers are, you can write down these simple mathematical equations. All right, so this was for alpha decay. Let's look at another example. Okay, so now they want us to do the beta decay of carbon-14. So again, we need to know what a beta particle is. So a beta particle is just an electron, right? So a beta particle is just E0 minus 1. And they give me the mass number of carbon, or of the particular isotope that we're using for carbon, but of course I need to go to the periodic table and see what the atomic number is. So I go to the periodic table, right, and I find carbon is atomic number 6. All right, so I've got my carbon-14. Then it's going to be spitting out this beta particle. Right, this was the beta. And then I just have to then figure out what the daughter is. And so let's use the math equation that I did last time. Right, so I'm trying to figure out what the new atomic number and mass numbers are. So if I do the atomic number first, I know that 6 is equal to minus 1 plus x, right? And so to solve that, I'd add 1 to both sides, right? And so that I get x is equal to 7, right? And then the mass number is easy, right? It's not going to change because I've got this 0 here, so I'm still going to have a 14 up top. And so take a second, go to your periodic table, and see what element has atomic number 7. All right, and hopefully you discovered that that was a nitrogen atom. So here's the nuclear equation for the beta decay of carbon-14. Okay, so now they want us to write the nuclear equation for the positron emission of scandium-44. So we need to know what a positron is, right? So a positron is the antiparticle of an electron, and its nuclear symbol, it's got the same mass, which is, basically negligible, right? No protons or neutrons, so its mass number is 0. But then where the electron is a minus 1, the positron is a positive 1. So this is a nuclear symbol for a positron. And I need to know what the atomic number of scandium is, so I'll go to the periodic table again. All right, here's scandium right here. It's number 21. So now I can write the nuclear equation. I've got scandium-44 right? It's going to spit out the positron. And then I've got to figure out what the new atomic number is, right? So 21 is equal to 1 plus x. So we see that x, in this case, is going to be 20. Again, because the mass number of the positron is 0, mass number is not going to change. And if you go to your periodic table, and hopefully you found that calcium is atomic number 20. All right, so we have just one last example.